Okay, okay, guys. So now, uh, yeah. So let's say you are. Well, today we'll talk. We'll discuss about this topic, binary search. Uh, so let's say you have a list of numbers. Okay, 12, 30, minus 100, 0, 45, 60, minus 22. So you have a list of numbers, and when we have a list of numbers or a set of numbers, how do you want to store them? What data structure? What structure you want to use to store them? Yeah, you can use an array to store them. Good, good. So you use an array to store them. So now the problem for you is you are given some number like 22, and we want to check if 22 belongs to this set. Check. So the question is check if 22 is in the list. That's the question. So if you want to have an analogy, like you have a stack of cards and you want to check whether a particular card is in the stack or not. So what can you do? So what is the simplest? You can check whether compare 22 against 12. 22 is not equal to 12. You go to the next element, 30. You compare 30 with 22 with 30. It's not, they are not equal. You keep going like that. So this particular approach is called as a linear search algorithm. This is what is called as a linear search algorithm. So what is the worst number of comparisons? Worst means largest number. Worst number of comparisons is n, where n is the number of elements in the list. So here n is 7. Good, good. And what is the best case comparison? This is called as worst case. This is best case. Best case number of comparisons is 1. Okay, like for example, 22 is the first element in the list. So you compare 22 with that element and it is there. It's awesome. No, then that's the best case number of comparisons. Now the question for you is, can you do better than n in the worst case? Can you improve the worst case from n to something else? Is it possible? How, Anusha? How? Binary search, huh? How can tell how binary search works? You start from the middle and then what happens? So that idea of binary search that some of you are familiar with, it doesn't work here because the list needs to be in a sorted order, should be in the increasing or decreasing order. Then only it is possible for us to use this idea of binary search. But but then, so we cannot improve the worst case, but let's say we can divide our list into 4 segments. Segment 1, segment 2, segment 3, segment 4, and we can assign segment 1 to 1 core. Another segment, all your processors, if you check, there will be 2 cores or 4 cores definitely for sure. So each segment we give it to a different core, and we can do parallel search. Parallel search. How much speed up do we get if we do a parallel search? We use 4 threads each each running on each thread running on 4 cores. Okay, you get approximately 4 times faster. So this is your first parallel algorithm. Okay, on my machine, it has 64 cores, and so I can get a 64 times speed up on my machine. So you can, this is how parallel, and if you in real world also, if you have a stack of 4, if you have a stack of cards and if 4 of your friends are there, if you are really searching for something, you can divide the stack of cards into, you can divide this stack of cards into 4. Listen, Gaurav, so it's very simple. So you have a stack of cards and you are searching for joker in it, okay? So you split the stack of cards into 4 parts. 4 friends are there. Each one of you search in parallel. Okay, the stack of cards within your own stack, whether joker is present or not. That's all. Nothing more than that. All right. So now what do you mean by another factor of 4? Why, Gaurav? It's very simple. There is nothing like sample space. There are cards. Split the cards into 4 parts, 4 friends. Each friend will look at his own substack or segment. Yeah, you can use less than max number of threads. You can even use more number of threads also, actually. Yeah. Don't worry about threads. It's just think of 4 threads, 4 friends. That's all. Okay. You will in the next semester, in your 4th semester, there is a course called as Programming for Performance. In that course, we will read this. We'll learn about this. Okay. So now, the point is, in order to improve, we cannot do better than this. So, by the way, there is, we cannot do better than this in the classical computational world using, classical physics. So, there is this area of computing called as quantum computing, in which there is what is called as a Grover's search algorithm. So, those of you, who think my lectures are boring and, it's all, you already know all this stuff, Grover's search. So you can spend more time in the quantum domain, quantum computation. Look at this. Yeah, I also don't know. It's yeah, it's for unsorted list ones. Yeah. So I also don't have good depth of knowledge in quantum computing to give a kind of some intuition about it. So I kind of leave it there. But this is like no fun. Okay, this is if you're all for all nerds in the class, not for us. Okay, let's go. Yeah, so now, so we want to do better than this in not in the quantum world, in this not using quantum computers, using regular computers. If you want to do better than this, then You know, we have to use binary search, but for binary search to work, we need to the list to be in a sorted order. So take the unsorted list and sort it. So you take this list and sort it, okay? So sort minus 22. Can you help me sort this list? Minus 100 is here. And after minus 22, we get 0, perhaps 12, 30, 45, and 60. Awesome. So now when you want to do, when the list is sorted, what we do is, you take this element 22 and go straight away to the middle element. This is a sorted list. This is the middle element. And you compare 22 with 12, and is 22 greater than, is 22 equal to 12? If 22 is equal to 12, then the search is over. 22 is present in the list, but 22 is greater than 12. So will 22 will occur in the left half or right half of this list? It will occur in the right half of the list. So you go to the right half, and then in the right half there are three elements, 30, 45, and you compare it with the, this is the first, this is the second, you compare it with 45, and 45 is the middle element. So 22 is not equal to 45. So will 22 will be in the left half or the right half within the sum? It will be in the left. So you go and check the left. So this is there. Now there is only one element. You compare it again as the 30, and then no, it's so 22 is not equal to 30. The search is over. You come out of the search space. So the idea here is, initially you have, yeah, good question. So let's see. Let's say sorting is for free, and then we will figure out what is happening. So initially, the element that we are searching for, it could be present in any of these positions in the array, 0 to n minus 1. Okay, that is, we keep on improving our hypothesis. Our initial hypothesis is, hey, the element that we are searching for could be present in any of the positions indexed from 0 to n minus 1. And we compare it with, so what we do, we compare, we take the midpoint. The midpoint is n minus 1 by 2, approximate midpoint. And we compare the element 22, okay, compare the element 22 with a of n minus 1 by 2. We make it into an integer. It's okay. It's okay. Yeah. The closest, round it off or floor it or round it or do something. We have to be careful there. Get the big picture. There are some details you need to work out when you write the code, and you could make errors there. Okay. So, but I will only give the big picture. Okay. And compare 22 with a of n minus 1 by 2. And if it is equal, then okay. But if it is, if 22 is less than, if it is less than, there are two other possibilities. 22 is less than or greater than. If 22 is less than a of n minus 2, what is the index range that we should be looking at? What is the index range? 0 to n minus 1 by 2. So on the contrary, if 22 is greater than that, then the index range that we should be looking at is n minus 1 by 2 to n minus 1. One important thing, so here, what is the size of the interval here? Interval size, interval size, this is what we call as root. this is a tree structure that we are drawing. The interval size here is n, and the interval size here is n by 2. In computer science, trees are inverted. The root is in the top, and and the leaves are in the bottom. Okay, so now let's say what we do, we take the middle element here and we compare we compare the element with so here this is what we do. This is our original thing. So we compare, and then let's say we focus our attention on sorry. So okay, so this this is the original thing. This is the midpoint, and no, so this is the green part and this is the blue part. So we will discard. So what we do is, when we come along this path, we discard the blue part and we just take the green part. So again, but if you can kind of, we can again divide. We will again divide this into 2. And so we can now say this is this color, and this is another color, and let's say based on our condition, it so turns out that we have to take this path. So we come to the orange segment here, and so on and so forth. So here if you look at the interval, this will be 0 to n minus 1 by 4. And here it will be n minus 1 by 2 to something like maybe what will be the range here? If we take the what will be the range associated with this? Yeah, maybe n minus 1 by 4 to n minus 1 by 2. Yeah, great. Thank you. So on and so forth. So the important thing here is, again, the size of the interval is n by 4. You keep going down, and finally you will stop the search when the size of the interval is equal to 1. That is n by 2 power k is equal to 1. So that is, you stop the search after you go down log n to the base 2 levels. The important thing is in algorithms, whenever you are discarding some constant fraction of elements, it's always good for you, be it half or 1/4 or whatever, it doesn't matter. If you are, as long as you are discarding some constant fraction of elements, it will do good for you. Constant fraction is right now half the elements we are discarding, right? Even if you discard 1/4 elements or or 1/10 elements or whatever that fraction all the time, then it's we are reducing the problem. During the problem of reducing problem size reduction, if you discard some constant fraction, it will be good. No, anyway, that's a side comment. Just focus on this binary search. So the important thing is, at every step you are discarding half of the problem. Initially we are discarding n by 2 elements. Here we are discarding n over 4, n over 8, so on and so forth. And do we take a particular path in the tree, or do we explore the whole tree here in this binary search tree? We take a particular path in the tree, and along that particular path we make k comparisons. So overall what happens is, in this case we have log n to the base 2 comparisons are invoked, and this is a reduction from, so earlier, so in the linear search, so in linear search versus binary search, in linear search we have n comparisons. in binary search, we have log n to the base 2 comparisons. How do we code this? Yeah, so let's we will see in the next class how to code this, but I would like you to figure out how to code this by yourselves. Okay. But there is a question. So let's say, take the case of your friends trying to yeah. So let's go ahead. But this is not for free, because in order to do binary search, we need to do sorting. We still didn't look at the sorting, but in order to do sorting, roughly we can say we require n log n comparisons are required. So if you see, yeah, you can using binary search, you require only log n, but in order to do binary search, you have to do a lot of hard work before. So does it make sense to go for binary search? Does it make sense to go for binary search? For large arrays, only when the array is already sorted. Yeah, Shivain got it. If we need to search a lot of times, then we can sort once beforehand. Yes. Because, like for example, your JEE marks, you keep checking again and again and again and again, but it wouldn't change, right? It will be the same. So, yeah. So, sorry, guys. It's I apologize if I hurt any one of you. Yeah, so it's so that's what it is. So because of when you search a lot of times, then so there is this comment, we got good JEE marks, that's why we are at AAATH. No, whether you got good JEE marks or rank or not, I'm sure you're all extremely wonderful students, and I'm very happy to be with all of you. That's just a bad joke. Let's move ahead. Yeah. So anyways, so n log n. So when like for example, take the other case of a stack of cards where you are looking for a joker. It's a one-time thing. You don't want to sort the whole stack just to find joker. It's not a good idea, right? So let's say if you are asking if there are case search queries, then yeah, so how much time is required in the two approaches using binary search approach? How much time, including sorting? Yes, sorting alone requires n log n. So for binary search, how much time is required? And for linear search, yes, we require n log n plus k times log n. We will see why n log n for sorting algorithms. And for linear search, it is k. So when is binary search? So when is binary search better than linear search? Okay. So binary search is better than linear search if Kn is greater than n log n plus k log n, just assume the base is 2 log n. Even if it is not, base is not that important. So it's so that is k is greater than n log n divided by n minus log n. Yes or no? So that is k is greater than log n divided by 1 minus log n divided by n. And as the value of n increases, as n increases, this tends to 0. So log n by n tends to 0. Then that means usually when you are thinking about large databases, where log n to n is very, very close to 0, it's essentially like when k is greater than log n, then you are better off going for sorting and doing a binary search. So here, log n to base 2 and log n to any base, when you compare them, they are not like much different. They are very equal to each other. Like when you have two friends who are compared, checking a stack of cards, one guy could be able to do slightly faster because he is good at cards, and the other may not be able to do with the same speed. But roughly, their strategy is the same, their order is the same. The story changes if one guy has a magical way of picking up, reducing the number of comparisons and be able to quickly say, hey, here you go. But otherwise, both of them are using the same strategy. One guy is able to do slightly faster than other, so it's okay. So in that sense, log n to the base 2, log n to the base e, log n to whatever other bases, roughly they are all the same because log n is log n. This is from algorithms perspective. N log n, there is sorting. We will learn about sorting in the next class. And so n log n, just take it, there are algorithms which can perform which can sort a list of numbers in n log n comparisons. So here, what is happening here is, if you look at the function n log n divided by n minus log n, if you take n common, then what happens is this gets transformed to log n minus log n divided by n. And the limit as n tends to infinity, that as n becomes larger, if the database, if the list of numbers is larger, you can see that log n by n, this becomes equal to 0 very quickly. Okay, so that's why I am saying, this function is for large values of n, you just have to focus. The growth is defined, the denominator is 1. The denominator is 1, the whole denominator is 1. So don't worry about the denominator, just look at the numerator. And sorting, I'm telling you, we will look at the sorting algorithms later, but we require n log n comparisons for sorting. And for binary search, n log n for sorting, this is for sorting. K is the number of search queries. K is the number of search queries. This is for sorting. This is for binary search. This whole thing. Are you all with me here? Does this make sense? Yes, when k is greater than log n, binary is better. I'm thinking maybe in the exam, midterm, some small analysis problems like this I may ask you. So Okay. All good. Shall I move on? Happy so far? So computer science is just not about Python programming, or you need to understand the analysis of the algorithms and see. Computer science is about feelings, huh? Vinkesh. Feelings. Or perhaps Vinkesh typed it in the wrong window. Okay, okay. All right, all right. So let's move ahead, move ahead. Okay, so now we are working on the other day Pythagorean triplets problem. So number one is yeah. Here we started with this. So hypotenuse. So if we fix a hypotenuse, number two. So yes. So we take side S1 and so the side S1. So from 1 to, yeah. So in this range we fix S1, and then we say we compute S is equal to H square minus S1 square. And now we want to check, step 4 is check if K is a perfect square. So what is the strategy that we followed? We followed, check if 1 is less than or equal to K, 2 times 2 is less than or equal to K, so on, so forth. I is less than or equal to K. And we want to try this for one I going from 1 to H. Okay. So that means there are H. So worst case number of comparisons, how many? Worst case number of comparisons. How many worst case number of comparisons? H minus 1. Okay. So let's write it as H. Okay. H minus 1, approximately H. And in the last class, we wanted to, we came up with a strategy to improve upon this. And we want it, that H to go down to log H. This is what it is. So what is the idea here? The idea here is we know that I lies between, if at all such an I exists, it should lie between 1 to H minus 1. So our initial estimate is I lies somewhere between 1 to H minus 1. And what we did is we set I is equal to H by 2 and check I star I with compare I star I with K. Compare I star I with K. So now there are, if I star I is equal to k, the problem solved. We figured out that k is a perfect square. But on the contrary, if I star I is not equal to k, there are two possibilities. If I star I is greater than, if it is greater than k, then what does it mean? Did we overestimate I? If I star I is greater than k? If I square is greater than k, is it an overestimate or underestimate? So if I square is greater than k, it means it is an overestimate. So when there is an overestimate, what should we do? This is I square greater than k, I square less than k. When there is an overestimate, we should go to the lower side. Yes or no? So we try to search from 1 to h power 2. And if I square is greater than less than k, this is an underestimate. And when it's an underestimate, we go from h over 2 to, we go to the right side. Does this make sense? Does this, again, this is the root. And these are the two children. So either we can go to the left or we can go to the right. And if you see the size of the interval size at the root is h. And here it is h over 2. And then, so again, we continue this process. We say we recurse. And this is what we are going to learn in the next class. Okay, we say we recurse, we repeat the same process. Yes or no? Recurse means apply the same process. What is h minus 1? Okay, I am just using a rough estimate. All these things you have to be careful. It's like h minus 1, h, it's like million and 1. Is there any difference between million and 1? If I say million and 1, no, it's painful. No, it's just root is the starting point. It's a big picture. Exactly, Manu. So what is happening is the interval size goes from h to h over 2 to h over 4 to so on h over 2 power k. So finally, when the interval becomes equal to 1, then either we know it's a perfect square or not. And then we get k is equal to log h to the base 2. And we take a particular path in this tree, and along the path we make k comparisons, that is log h to the base 2 comparisons. Okay. So now you can very well appreciate that how we can go reduce the number of comparisons from h to log h to the base 2. Are you all with me here? Does this make sense? Yes, no? Yeah, approximately it is h minus 1 by 2 or no, you have to, the interval you need to figure out exactly, but roughly I'm giving the rough intervals for you. Is it okay? Okay, I'm just giving. No, this is better. No? Clearly, we are having for a particular value of S1, we are trying to do this. And then I want you to focus on, forget about Pythagorean triplets problem. That's a motivation. I want you to understand the technique, how we can get away with linear search and how we can use a binary search here. We will still use 3 loops, but the innermost loop is, it doesn't take n, it takes log n time. No, linear search doesn't have h square comparisons. It is, we only go till h because okay. Abhinav has an idea, instead of using I less than h, we can use I less than S1. Good idea. Yeah. That also saves time. So I hope you all understood what Abhinav mentioned on the chat box, that instead of using I less than H, use I less than S1. So that way repetition won't occur and time is reduced. Very good idea. I less than S1 or I greater than S1 or either way, it's okay. Are you all happy so far? Doing good? This is a very important, guys. This is a kind of a milestone, an important milestone in okay. So now let's move on to the next topic. In the last 10 minutes, I would like to cover. Let's say we are working with polynomials. Let's say you want to, there is a polynomial 6x cube 4x square plus 2. So the question is, there are two questions I want to ask. What is the input format and what is the storage structure that you use? Input format and storage structure. So the input format, so don't try to, so there is the important thing that you have to understand is when you are trying to solve some real world problems, okay, be it trying to compute the value of a polynomial, root of a polynomial, or model some thing, we need to come up with a suitable representation structure in the computer and also an input format structure. So there is no point, it's not necessary for you to give the input as 6x cube plus 4x square plus 2. You may just give the input as you just give 6, 4, 0, 2, and you just use array. In an array you just store a of 3 is equal to 6, a of 2 is equal to 4, a of 1 is equal to 0, and a of 0 is equal to 2. So this is one input format that you can use for supplying for inputting a polynomial. Or other way also you can do, instead you can give 2, 0, 4, 6. Okay, so either way you can you take the input in some form and either format 1 or format 2, and this is the same storage structure that you use inside. Is there an alternate way, a third way? Can you think of a third way of providing the input format? A third way is, degree 3 term, it is 6, the coefficient is 6. Degree 1 term, the coefficient is 0. Degree 2 term, the coefficient is 4. Degree 0 term, the coefficient is 2. Okay. So this first column is the degree of the x variable and the second column is the corresponding coefficient. This is coefficient, this is not, I am calling it as column, but at the keyboard you give the input like this, 3 space 6, in meaning 3 is a degree and the corresponding coefficient is 6, so on and so forth. Does this make sense? Can we take this one and kind of, with this format, you actually don't need to supply this. That degree 1 term coefficient is 0, you can just assume that all coefficients are 0, and then later only you just use the coefficients of the degrees that are supplied. You don't need a 2D array, you just need 1D array. You just again, this gets stored in the same linear array form. You don't need a 2D array for it. Are you all with me here? This is a very important idea that when you are supplying, similarly, when you are working with, yeah, before I go there. So now once you store a polynomial, if I ask you to write a program to compute the differential of a polynomial, will you be able to write a program to compute the differential of a polynomial? Yeah, so you have to think about it. Okay, so in the third, so there is this question in the third method, we don't store 3. When you read 3 and 6, we go and say, when you read this from the keyboard, you just say a of 3 is equal to 6. Yeah, that's all. A of degree is equal to coefficient. That's it. Thank you, Shreyesh. Sir, we can shift coefficients from I plus 1 to I. Good, Argya. Yeah. So very good for differential. Perfect. So this particular idea of when there is a problem to solve, what is the representation structure, what is the input format for it, and how do we so Anika, the answer is already given in the chat box. You take a look and you should try it again later. Think about it and try. So what is the input format for it? What is the internal storage structure for it? These are the fundamental things that you need to design. Think about when you are trying to solve a problem. Similarly, one more example, when you are working with systems of equations, 2x plus 3y is equal to minus 6, x minus 2y is equal to 10. So let's say when you are working with systems of equations, what is the input format here? Input format, how can you give this? Input format could be 2, 3, minus 6, 1, minus 2, 10. So this could be an input format. And what is the internal storage structure? What is the internal storage structure? The internal storage structure is you can use a 2D array. Excellent. Yeah. So now once you have the input format and once you have the storage structure, then we can read the input and you can store it, and then you are ready to do manipulations on it, do computations on it. Okay? Are you with me here on this? All good? Trying to conclude today's lecture here that this with these ideas. You can think of different alternate representations or inputs, but this is one way we are seeing. Anika, it's not 2D array is not a good choice for the method 3. It's not a good choice. There is others way by using structures. We will discuss, think about it. No, it's 2D array is not a good choice for this problem. For polynomial, you don't want to use a 2D array. This is the 1D array problem. Because we are using k queries, Gaurav. So that's the reason. For one search it is n, for k queries it is kn. Okay, I think I would like to conclude today's lecture.